All right, welcome back to Computer Science 305. This is the fourth part of the first lecture on Prolog. And so we're going to continue on. We're going to talk about negation and failure, and then finally ending with what is Prolog good for? Yay. All right, so the not predicate, if we were to escape this, and then, so not gives us, when we're looking at the simplest applications, it often works quite a bit like bit-based logical negation. So let's say we have member 1, 1, 2, 3. So we're checking if 1 is a member of the list provided, and in fact it is. Then if we want to run, if we use the predicate not, we would say not member 4, 1, 2, 3. That returns true, right? Why? Because 4 is not a member of 1, 2, 3, and so not's going to negate that value. So member 4, 1, 2, 3 is false, and not is going to negate that. Interestingly enough, that is not what's showing here. I think what they meant to say was not 1, 2, 3, 4. If we do that, then it returns false. So there's a procedural side to this, right? Negation is failure. To prove not X, Prolog attempts to prove X. Not X succeeds if X fails. So declarative not of X is equivalent to the logical negation of X, but procedurally, not X succeeds if X fails, right? It fails if X succeeds and runs forever if X runs forever. So bear this in mind. There's a procedural aspect to negation. So we can run an example, right? We can create, if we go back to our relations database, we can create sibling. So we say sibling x, y. If we say not x equals y, and parent p x and parent p y. So if we did this, right, in this form, and we load it up, we'll say, actually I'm going to kill this, rerun this, consult, and we say relations. Then if we run sibling Kim Kent returns true. If we run Kim Kim, it comes out as true. And then if we run XY, right? So we're asking if there's anywhere that there's a sibling such that X and Y, there's any place that X and Y are siblings, we come back as false. Now, interesting as that is, right? Because it checks this not equals Y first, and if that's false, it just is always false, right? So the problem here is that in reality, what we might want to look up is if we adjust the order of sibling such that not comes after all these, the parent relationships, then we get, we might be able to see that there are a potential component to this. So let's go ahead and we'll reconsult this. Let's see, can I find? Yeah, there it is, sibling XY. So we get Kim Kent, right? So the question is Kim and Kent actually siblings? Well, in fact, they are. Margaret is the parent of both Kim and Kent. So apparently they actually are siblings. So we had a problem with our original definition. And we can continue along, and we find that Kent and Kim, right, are siblings, of course, and Margaret and Jean, right? Because Herbert is the parent of both Margaret and Jean, and so they must be siblings. And let's see, we get Jean and Margaret, of course, and that's it, right? So the interesting thing here we have to understand is that because not has a procedural aspect, we ran into some problems there. And you just need to bear that in mind when you are developing your different rules. And so the final part here is we have to ask ourselves, what is Prolog good for? And so this gets us into this classic riddle, right? A man travels with a wolf, goat, and cabbage, wants to cross a river from west to east. A rowboat is available, but only large enough for the man plus one possession. So the wolf eats the goat if left alone together. The goat eats cabbage if left alone together. How can the man cross without some sort of loss? Right. And so we can actually utilize Prolog to describe these configurations, right? So we represent a configuration of this system as a list showing which bank each thing is on in this order: man, wolf, goat, cabbage, right? So the initial configuration is we're on the west bank, so everything is on the west bank. And so if the man crosses with the wolf, the new state is EEWW. But then the goat eats the cabbage, so we can't go through that state. Our desired final state is EEEE, right? Everything's on the east bank. So then we can define that there are moves, right? So in each move, man crosses that most one of his possessions, and we can represent these four moves with the four atoms: wolf, goat, cabbage, or nothing. And here nothing indicates that the man crosses alone in the boat. So, so moves transform configurations. So each move transform one's configuration from another. So in Prolog, we can write this as a predicate: move, configure, move, next configuration, right? So a config is a configuration like the list www. A move is a move like wolf, and next config is the resulting configuration. In this case, EEWW. So we can then define this, right? So we'll define this. New file, we'll call this puzzle.pl. And so we can create this, right? We'll create change EW, and the second one WE, right? So this is going to be used to construct these moves, right? A move is always just a change from one thing to another. So we have a move, predicate move that takes in X, goat, cabbage, right? And then wolf, and then Y, goat, cabbage. Which then is saying we're going to change X and Y. Right? Because basically this first one is saying that we're going to just leave goat and cabbage alone, and we're moving the wolf and the man to the other side. And then we have move X, wolf, X, cabbage, and then we're moving the goat, and Y, wolf, Y, cabbage, right? And again, we're just doing a change XY. And then again, move X, wolf, goat, X, and this time we're moving the cabbage. And so it's Y, wolf, goat, Y. And then finally we're going to define a predicate move such that we're moving the wolf, the goat, and C, right? This is the nothing move, so nothing changes except for the man, right? He just went back and forth. Okay, very good, right? So this is the move predicate that's defined now. And so we have safe configurations, right? So a configuration is safe if at least one of the goat or the wolf is on the same side as the man, and at least one of the goat or the cabbage is on the same side as the man. So we need to define this. So we can do this. So we have 1 EQ x underscore, and then 1 EQ x underscore x. And so we can call something safe. So we have the configuration man, wolf, goat, cabbage, such that 1EQ man, goat, wolf, right? So as long as the things that destroy each other are with the man at any one time. So the goat and the wolf must be together with the man because he keeps them apart, and then the goat and the cabbage must be, if they're on the same side, must be with the man because he prevents the goat from eating the cabbage. Okay, so 1EQ man, goat, cabbage. Okay. So now that's all good. Let me come down here. So the solution, right? A solution is a starting configuration and a list of moves that takes you to EEEE, where all the intermediate configurations are safe. So let's define a solution. So we can define a solution. Right, given the empty list, right? Solution, so we have a config, and then we have a move, rest, such that we have move, config, move, next config, safe, next config, and solution, next config, rest. Right? Okay. So basically what we're saying here is that we have a solution if they all land on the east side of the bank and there's no more remaining configurations. Oh, sorry, no remaining moves. Or we have a solution with a config and a list of moves. Such that a move from config, move, and next config is safe, and the solution next config rest is true, right? So so let's find a solution. We will start with, all right, we'll load this up. So we'll say consult puzzle, and I have a singleton. Oh, my bad. I accidentally misspelled goat. Consult that, and then we say length x7 and solution our initial position and x, right, the actual solution. So we're looking to see if we can, we're restricting with the length of x, right? So the length of the final solution, the move list, is that we were restricted to no more than 7. Without that restriction, Prolog won't find a solution, right? It gets lost looking at all possible solutions like goat, 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 on forever. And so we'll see more about this in Chapter 20 on why we can get around that. But if we run that, we see that I get some sort of... oh, my bad. I tried Y, not capital Y. Okay, there we go. So we can get a... basically, it's going to continue on for the rest of time, giving us the same solution over and over. But anyway... as we can see there, it solved that problem. We can define... So basically what we're doing here when we define this program is we literally just described all the things that would make this... the things that are necessary to make this possibly true. Right? We defined safe, we defined solution, what these things would look like, and then using that, we allow the Prolog system to figure out the answer for us. And this is the whole gist of declarative programming. And so this leads us to what is Prolog good for? And so the Prolog, if the program can specify a logical problem, right? So if we have some problem and we can logically define it, we can then use Prolog. We can write a Prolog program to declaratively stating that problem and what its solution might look like. We can let Prolog search that solution space to find a solution to the actual problem that we pose. And so if you can figure out how to do this, or if you have this type of problem, then Prolog is going to be what you want to use to solve it. And that's kind of the gist of what we're doing here. Anyway, so that's the end of this lecture, and I think the Prolog lab will be up on Wednesday, and we'll have some interesting problems to solve. So I look forward to talking to you all then. Have a great day.